For millions of years, the oceans were a world within themselves, teeming with life, full of beautiful sea creatures. The ocean means many different things to different people. They cover around 90% of the Earth's surface. From what we cannot see, that includes the microscopic fauna, to the beautiful things we can, like invertebrates of corals, fish, and large mammals. They all live harmoniously within their very niche space that defines their very glory and beauty. The ocean and its inhabitants collectively so mesmerizing and captivating, full of grace, unique to its very own. The world's population is on the rise and growing rapidly at a rate that has never been seen before. As a result, the oceans are suffering from both direct and indirect misuse that threatens our very unique oceans and the beauty of its inhabitants. What would happen if the ocean's inhabitants disappeared? What would happen to our oceans if it could no longer support our growing population? What would we eat? What would hundreds of millions of people earn a living? What kind of experiences would our children have with no ocean, no coral reefs, or fish to see? Our actions are driving irreversible change that sees our oceans in serious jeopardy. The changes on the land we make see our carbon footprint increase, and this has direct negative repercussions to our oceans. We have reached a point now where we have used the oceans and they find themselves at their very limits. We have reached a tipping point. If we do not do anything now, we not only have a crisis for the ocean's survival, but also for humanity's survival. The problem of ocean acidification has only come to light within recent times that was derived from a consequence from climate change. The increase in carbon dioxide within our atmosphere is driving climate change, which in turn is increasing the temperature of the oceans but is also changing the chemical processes within them. They are both related and driven by the same thing: climate change. The ocean has absorbed about 30% of the carbon dioxide emitted into the atmosphere from anthropogenic sources. This has resulted in changes of the ocean carbonate chemistry. This is very important for things like coral reefs and other organisms like clams. Ocean pH has already decreased by a global average of 0.1, and unmitigated carbon dioxide emissions will cause the ocean's pH to decrease by as much as 0.4 by the year 2100 and 0.77 by the 2300. The amount of carbon dioxide emissions we have pumped into the atmosphere since the Industrial Revolution, much of it has ended up in the ocean. This is not good. When carbon dioxide and seawater meet, the chemistry is very straightforward. The repercussions, however, gradually become devastating. Let's look at the fundamentals of the chemistry that occurs that drives ocean acidification. The acidity of any substance on the pH scale is measured by the amount of hydrogen ions in solution, or the hydrogen ion concentration. pH is measured as the negative log of hydrogen ion concentration. The bottom line here is, when there are more hydrogen ions in solution, the more acidic it becomes. A decline of 0.1 pH units might not sound like a lot, but on the logarithmic scale of pH, it translates to about a 30% rise in acidity. A change in 1 unit change represents tenfold. This is huge in relative comparison to the size of the ocean and how big of a change is experienced. When measured on the pH scale, the world's ocean has been around 8.2 for over 300 million years. This means our oceans are moderately basic rather than acidic, but in the last 200 years, that level has dropped to 8.1 on the pH scale and set to be projected to be even lower as the coming years. When carbon dioxide is absorbed by the ocean, it dissolves into the water. The dissolution of carbon dioxide can lead to the formation of 3 species of carbon: bicarbonate ions, and carbonic acid. Together, these 3 species are often referred to as dissolved inorganic carbon, or DIC. Carbon dioxide enters the water through the interface. It then chemically reacts with the water to produce carbonic acid. Carbonic acid dissociates and splits up into its ions, producing a hydrogen ion and bicarbonate ions. The ocean naturally has carbonate and bicarbonate ions in it, but when hydrogen is added to carbonate and bicarbonate, it creates carbonic acid, which then further dissociates into carbonate ions and releases another hydrogen ion. Therefore, ultimately, for every carbonate ion produced, there is 2 hydrogen ions produced. The hydrogen ions produced are the causing factor for the lowering of the ocean's pH and thus increasing the acidity. The more carbon dioxide that is absorbed in the ocean, the more hydrogen ions are created, further lowering the pH of the ocean. Let's look at this simple simulation to clarify the chemistry behind the ocean acidification.
For this experiment, we're going to use demineralized water, and this will act as our ocean. If we test the pH of this water, (7.3). Now I'm going to use this same water and I'm going to fill up a SodaStream bottle. And for the purpose of the experiment, we're going to use a SodaStream machine to replicate how carbon dioxide enters the interface of the water and creates our ocean acidification. Now, if I test this same water after the CO2 has been pushed through, we get a much lower reading.
The effects of ocean acidification is expected to impact ocean species to varying degrees. Photosynthetic algae and seagrasses may benefit from higher concentration of carbon dioxide conditions in the ocean as they require carbon dioxide to live just like plants on land. On the other hand, however, studies have shown that lower calcium carbonate saturation states can have dramatic effects on some calcifying species, including oysters, clams, sea urchins, shallow water corals, deep sea corals, and calcareous plankton. Today, more than 1 billion people worldwide rely on food from the ocean as their primary source of protein. Thus, both jobs and food security around the world depend on the fish and shellfish in our oceans. If ocean acidification continues at the rate that it currently is on, then most of the jobs and food security around the world will be in serious jeopardy. Many calcifying species exhibit reduced calcification and growth rates in laboratory experiments under high concentrations of carbon dioxide conditions, and this is very much evident in the ocean, whereby these species lack to grow at a rate that matches times before ocean acidification was present as a result of climate change. Ocean acidification also causes an increase in carbon fixation rates in some photosynthetic organisms, both calcifying and non-calcifying. Past mass extinctions events have been linked to ocean acidification. However, the current rate of change in seawater chemistry is unprecedented. The ability of marine animals, most importantly petrapod mollusks, foraminifera, and some benthic invertebrates, to produce these calcareous skeletal structures is directly affected by seawater and the carbon dioxide chemistry, by which it can dictate and change dramatically. Carbon dioxide influences the physiology of marine organisms as well as through their acid-base imbalance and reduced oxygen transport capacity. The few studies at relevant saturated states of carbon dioxide levels in the ocean impede our ability to predict future impacts on food web dynamics and other ecosystem processes. Coral reefs were one of the first ecosystems to be recognized as vulnerable to ocean acidification. To date, most scientific investigations into the effects of ocean acidification on coral reefs have been related to the reef's unique ability to produce great amounts of calcium carbonate. It has been estimated that the main reef-building organisms, corals and calcifying macroalgae, will calcify 10 to 50% less relative to pre-industrial rates by the middle of this century. This decreased calcification is likely to affect their ability to function within the ecosystem and will almost certainly affect the workings of the ecosystem itself. However, ocean acidification affects not only the organisms but also the reefs they build. The decline in calcium carbonate production, coupled with an increase in calcium carbonate dissolution, will diminish reef building and the benefits that reefs provide, such as high structural complexity and the support that it provides on biodiversity on reefs, the breakwater effects that it has to protect shorelines and create quiet habitats for other ecosystems such as mangroves and seabeds. Whereas the effects of ocean acidification on the calcification of adult reefs is increasingly well documented, effects of early life history stages are largely unknown. Coral recruitment, which necessitates successful fertilization, larval sediment, and post-sediment growth and survival, is critical to the persistence and resilience of coral reefs. Fertilization settlements of corals, the growth, were all negatively impacted by increasing dissolved carbon dioxide in the water, and the impairment of fertilization is thought to affect a lower sperm concentrations of coral. Ocean acidification has the potential to impact multiple sequential early life history stages, thereby severely compromising sexual recruitment and the ability of coral reefs to recover from disturbance such as ocean acidification. Ocean acidification is an emerging global problem. Over the last decade, there has been much focus in the ocean science community on studying the potential impacts of ocean acidification. Since large efforts to monitor ocean acidification worldwide are only just beginning, it is currently impossible to predict exactly how ocean acidification impacts will move throughout the marine food chain and affect overall structures of the marine ecosystem. By 2050, however, both population increases and changes in carbonate mineral saturation states will be greatest in low latitude regions, multiplying the stresses on tropical marine ecosystems and societies. With the pace of ocean acidification accelerating, scientists, resource managers, and policymakers recognize the urgent need to strengthen the science as a basis for sound decision making and action. This is to reduce our carbon emissions that accelerates the effects of climate change and thus mitigating the effects of ocean acidification as a result. Political will and significant large-scale investments in clean technologies are essential if we are to avoid the most damaging effects of human-induced climate change that results to ocean acidification. In order to fundamentally address the threat of ocean acidification, environmental managers need to know where, when, and by how much changes in coastal ocean carbonate chemistry will influence human livelihoods and what they can reasonably do about these effects. Globally, addressing ocean acidification and its impacts requires international agreements to reduce rising atmospheric carbon dioxide concentrations. The link between ocean acidification, climate change, and the United Nations Framework Convention on Climate Change, or the UNFCCC, should be of top agenda, whereby possible scenarios for developing common solutions to reduce and adapt to ocean acidification and climate change are offered. Areas where the UNFCCC is currently lacking capacity to effectively tackle rising ocean acidity should be addressed immediately if we would like to save our precious oceans and the unique organisms within them that we as humanity so heavily rely on.